Hey guys, this is the second online lesson for Math 20-2 in statistics. So the first page says, or the first page of this says, the normal distribution investigation. So usually um, we actually do this all together, where I have a whole bunch of dice and we sit and we roll it. But I'm not going to ask you to recruit dice from your house. I have just a technology way of doing this. So usually what we do is I tell you to roll your dice 20 times or 50 times and fill in the table for the sum of it. So you roll 2 dice. I'm going to go to this page. So if I were to roll 2 dice one time, hopefully this is going to work. Okay. Roll one time. Okay, I rolled it one time. I got a 2 and a 6, so that sum was 8. And I roll it again. One time. Oh, now the sum is 5. So it's plotting these out. Usually what we do is we just do little ticks on the table next to the sum, and that gives us our frequency. So I rolled it another time. Oh, I got an 8 again. 3 and a 5. It doesn't matter what the individual dice are, but the sum is 8. So I roll it again, and again, and again, and again, and again, and again. So I'm rolling it one by one, getting up to 20 times. So what I would do for my table is I would put in the sums of each of those. I can't do it with the 2 different screens, but for a sum of 2, I would put 1. And for a sum of 3, I would put 2, a frequency of 2, so it happened twice. For 4, you see I didn't get any. For 5, I got 2. For 6, I had it happen 3 times. For 7, once. For 8, 5 times, and so on and so on. And so that was my 20 rolls. And then I would have you guys each do your 20 rolls. And so you see your chart maybe looks a little different. So 1, no 3s, sorry, 1, 2, no 3s, 2 4s, and so on. And so that was person B's 20 rolls, and then I would have person C do it. Oops. And that would be their information, and so on. And so then what we usually do is combine it all as a class set. So let's say that there were 5 people, and we all did 20. That would give us 100 rolls. And so if we combined all of our data pieces, again, for the class table, if we had 100 rolls, we have 3 people that got a roll of 2. So you can fill this in if you want to do that as our class table, or just kind of watch along here. You might need to pause it because I might not leave it up long enough. But we see it kind of goes up. There's a little bit of weirdness here, but that's just because it's a random process, right? Of those 2 die, it could land on any of the 6 sides at any point. We could actually have 100 dice rolls that were equal to 12. It's very improbable, but it could actually happen that we could have all 100 here, or all 100 be equal to 2. Or we could have it evenly distributed, that they were all the same value. Any of those could happen. So as we add on more dice rolls, what we'll see, so I'm going up by hundreds and I'm at 1,300, is if I start adding on 10,000 at a time. So you can see that the shape of it now is no longer changing. I'm gonna reset it and start with ones. So you see that the shape of it is kind of changing every time, right? Like this one was getting taller for a bit, and then this was. If I start going with 10s, we see the shape, it's kind of growing in the middle more than it's growing at the ends, but then we'll see something that it grew more over here than it did on this side. If I start doing it by 100s, we see that it's higher up here, but still a little bit of a difference. It seems like there's a couple more on the high number side. Then it looks like a couple more ended up over here. So once we start getting more and more values, so if I start doing the 10,000s, you see that the shape isn't really changing. That's the highest in the middle. And then if you look across, so the highest value is at 7. If you look across, the bars on either side are usually pretty close. So 15,376, 15,304. Then if I go one more bar over, so looking at 5 and 9, 12,392, 12,190. Then if I go all the way to the edges, so a value of 2, meaning both dice needed to be a 1, and a value of 12, meaning both dice needed to be 6. So this is 3,001, and this is 3,020. And so again, as we keep adding on 10,000, it stays pretty consistent in the shape. So we've done 380,000 rolls now. So that's what it's looking at. So this distribution is kind of what we're looking at. So I'm just going to flip back to this. So you can fill out any of the table. If you want to look at that dice simulator, it's called GeoGebra. So I always just search GeoGebra, and then I just type the word dice, and it'll come up with this scenario that you can kind of play around with if you wanted to fill in that table. So yeah, usually we do the class table, and then we would draw kind of a histogram table. Where we would have the sum. So on that chart you saw it showed a sum of 1, but there's no way for you to roll 2 dice and get a sum of 1. So 2, ooh, sorry, that's at a weird angle, through 12. And again, if we graphed it out, I'm not doing each of the individual bars, but it got kind of a shape like that. Sorry, this is better spaced out in your booklets, I believe, than in mine. So the first question, or in this set here, so it says, how does increasing the sample size affect the distribution of the data? So for this first question, oh, I'm trying to write on my computer instead of on here. So if we increase the sample size, so when I was pressing the 10,000 instead of the 1, when I did way more, what we saw is if we increase the sample size, we will have more data. More data points close to the mean. And more consistent data. So what I kind of mean by that, I'll come back to this page in just a second, is if we did 100, you see the shape here. So we have kind of 2 peaks in this one. So we have 17 at 7 and we have 15 at 10. So we have 2 peaks. It doesn't quite have that nice distribution because it goes down and then it goes back up. And if I reset it and did 100 again, we see, holy moly, I have all these low values. Because again, our sample size is really small. It would be even more different if I did 10. Okay, so I have some 2s and 1s. No 9, no 11 and 12. If I reset it and do a 10 again, whoa, now I have no 2 and 3 or 10, 11, and 12. So our shape looks very different when we have a small sample size versus when I do this a whole bunch of times, it will look the same. So I did 120,000 there. If I did it here, it would look very similar for that. So that is what we're talking about when we say we increase the sample size. We'll have more consistent data. And the next part says, what do you think a graph, oh, I guess we've kind of done this. So what do you think a graph that represents 100,000 rolls of 10 dice would look like? We were doing 100,000 rolls of 2 dice. It's giving us kind of the same idea, but what it would look like, just to give us an idea, is that same sort of shape. So bell-shaped is what we will call it. The highest frequency, oh, sorry, I'm writing on a weird angle. Highest frequency around 7, and lowest frequency at 12 and 2. So the highest frequency around the mean and the lowest frequency at kind of the edges. So as it says there, I don't know if I copied this. Oh, no, it's up here. So this graph is called the normal curve. As the number of rolls increases, the graph approaches the normal distribution. Notice that the normal curve is symmetrical around the center. This means that 50% of the data is to the left of the mean and 50% of the data is to the right of the mean, or the center, I guess is how I'm defining it there. So that's a normal distribution. So now we'll go into, so if you flip over to the next page, it says page 21 at the bottom. This is that statistics workbook that we've kind of been looking at. And it says 6.3 normal distributions at the top. So it says explore. Mathematicians have found that the mean and standard deviation of certain types of data over a long period of time can offer very specific and useful information about how spread out the data really is. You may have noticed similar shapes of the histograms we've made. An entire school was asked to rate the fries at Restaurant C. So now we don't just have the group of 17 friends, but a whole high school was asked to rank the fries at Restaurant C, and the results are presented in the histogram below. Let's look at the shape a little more closely. So what it's saying here, just to give us an idea, is draw a dot at the top and in the middle of each bar. So if we draw a dot here, and here, and here, and here. It says join these dots together with a smooth curve. So joining the dots together with a smooth curve. Ooh, sorry, this is so hard to do on the tablet. That's the best I can really offer you right now. Continue the pattern to the left before the bars start. So that's why I kind of kept going there and to the right of the bars. So that's what we're talking about with our normal distribution. It says, how would you describe this shape? So you could say that it's pretty symmetrical. Once you have a big enough sample size, at least, as we saw when I only did 10 dice rolls, it was definitely not symmetrical. When I did 10,000, it was quite a bit better. So symmetrical, shaped like a bell. So you can see what I mean in kind of that next, like right down below that. Just give you a second. So it says gathering information. This shape that you drew is called a normal curve or a bell curve because it has a shape similar to a bell, if you know what a bell looks like, but we usually just call it a bell curve. So things that make such a shape when they are graphed are said to be normally distributed. It's been discovered that among large groups of individuals, many naturally occurring events are normally distributed. So for example, something like height is normally distributed because it's continuous, right? Masses of people, so how much people weigh, is normally distributed. You have people that are heavier and lighter, and you're going to have more people grouped around the mean. Foot sizes, IQs of large groups of people are all normally distributed. So on to the next one. This is on to page 22 in your notes package. So it says, furthermore, many characteristics of modern mass production are normally distributed. For example, in manufacturing something such as hockey sticks, very rarely are any two sticks exactly the same. They'll be pretty darn close under casual observation, but a closer look would reveal that they might be a little bit different in mass, a little bit different in length, a very small difference. And so these differences tend to be normally distributed as well. So the example that we had the other day was like bags of potato chips. It's not perfect. You've all got a bag of potato chips if you eat potato chips. That's like way too empty, and then you've potentially got one that seems a little extra full, which is pretty sweet. So again, this mass production thing tends to have these normally distributed differences in some type of measurement. So anything that is normally distributed is always grouped in a very specific way. And so these Like, I can't put enough stars on these pages for you guys. This specific way is quite important within this unit. So, number one, it says about 68% of the data lies within 1 standard deviation of the mean. So again, our mean being that x bar. If we took our mean and added 1 standard deviation or subtracted 1 standard deviation, this amount, sorry, I need my colors. Let's go back. So if we went 1 standard deviation above the mean and 1 standard deviation below the mean, you're just going to have to accept these mu's because I'm going to forget to change them. So mu is another way of writing that x bar or mean. So this area that I'm going to color in, I guess it's colored right to the right, represents 68% of the data. Is 1 standard deviation above or below the mean. So if you can think about that, that means that 34% of the data should be 1 standard deviation above the mean, and 34% of the data should be 1 standard deviation below the mean. So those two numbers add up to 68. Oh, and that's what it's kind of saying on this side here. So 68% of the data under the curve is this shaded area, so 34% on each side. So again, this is the mean. Whatever your value for standard deviation is, if you go 1 above or 1 below, that's going to get you 68% of the data. I should move this down. So this means half 68, which represents the 34, is to the left or below, and half is to the right or above your mean. So on to the next one. About 95% of the data lies within 2 standard deviations of the mean. So if this is our mean, I'm actually trying to write up and down and it won't let me. There we go. So 2 standard deviations above or 2 standard deviations below represents 95% of the data. So we know, I'm going to kind of color over on this one, that 1 standard deviation above or below is 68%. And then if we go 2 standard deviations above or below, this represents 95%. So we could actually figure out as well what that would be equal to. Let's do green here. So we know that if we go 95, subtract 68, sorry, I don't know why I'm putting this in a calculator. So that's 27. So what the 27% is these 2 green areas, because we know that this is 34 and this is 34. So all together, this green area represents 27%, because that would be 68 plus 27 is equal to 95. So we could actually figure out what each of those little green areas, trying to work on the tablet and the computer is too much for me. So if we did 27 divided by 2, that's 13.5. So each of those green areas represents 13.5% of the data. And so we know from there, sorry, I need another color. I'm just going to do red. If we've covered off 95% with this green and blue, this red portion, so this red portion that's right here, oh, whoop, this red portion would represent 5% of the data, because this is 95% of the data. These two little tails on the end represent 5% of the data. And finally, full screen, our third rule. So about 99.7% of the data lies within 3 standard deviations of the mean. So if this is our mean, if we go 3 standard deviations above, so mean plus 3 standard deviations, and 3 standard deviations below, this now represents 99.7% of the data. So I'm not going to go switch back the colors, but we know 1 standard deviation was 68, 2 was 95, 3 is 99.7. So that would leave in these two little tails, if we just look at those two little tails, that would be 0.3% of the data would be left over between those two tails, or 0.15 and 0.15. That's what each of those would be worth, is 0.15%. So 99% is this blackened part. So that means our leftover is 0.3 if we divided those both in half, 0.15 on either side. So these 3 numbers are important. You're not given them, but you do kind of need to know them. So the grand conclusion kind of wraps it all up nicely. I'm going to get my colors again because I like to represent it that way. So I think we were doing blue first, right? So the mean plus or minus 1 standard deviation is 68. The mean plus, I'm going to go all the way across here, or minus 2 standard deviations is that 95. And the mean plus or minus 3 standard deviations is 99.7. And so we figured out these numbers here. So 34 and 34 is half of 68. This 13.5 we figured out as well, because if we subtracted, so 95 subtract 68 and then divided that difference, which was 27, in half, it was 13.5. And then finally, we know that this amount, 2.35, if we did 99.7 subtract 95 and then divided that by 2, that gives us each of those pieces. And then finally, our leftover little tails there. So beyond 3 standard deviations above or below is 0.15. So that's outside of 3 standard deviations. So on a quiz or a test, you won't really be given this piece of information. I had a student a couple of years ago, and for the statistics unit, it's amazing. You'll see kind of in the next section, she would plot out this graph every time. I don't know how she did it all in a reasonable amount of time, but she found it really useful to plot out this graph, knowing these percentages, like all of those specific percentages. And then from there, when she had her mean and her standard deviation, she could actually fill in what each of these particular pieces actually represented. It's really interesting. It's going to be faster to put stuff in your calculator once we look at standard normal stuff, but she always plotted it out, and I always found it very beautiful that she could do that every time. So again, this chart is super important. I guess there's more below here. It says the graph would be symmetrical about the mean, meaning if we folded it over at the mean here, so that's the mean there, if we folded it over, the 2 parts of the graph would be mirror images to one another. And then this 68, 95, 99.7 rule, important. So 68 is within 1 standard deviation. Again, that's above or below the mean. 95 within 2 above or below, and then 99.7 within 3 above or below. Since 100% of the data is under the curve, we say the total area under the curve is 1, representing 100%. The curve approaches the x-axis at both ends, but does not actually technically touch it. It should go on forever, or it goes on quite significantly further than you would actually see. So in conclusion, every normal distribution can be precisely described by its mean and its standard deviation. So let's look at this with actual values now. So I told you guys to make sure that you did the questions from the last lesson, because, as I mentioned, it would come back again. So in the last lesson, we had the case of a local electronics store which wants to sell protective cases for an MP3 player that is 70 millimeters long. The owner has a choice of buying the cases from two different suppliers, so from supplier A and supplier B. And so we have some data about their production. So the mean length of the case from supplier A is 71 millimeters. The mean length of case from supplier B is also 71 millimeters. So those are the same. But where our difference comes is our standard deviation. So our standard deviation from supplier A is 0.33 millimeters, and our standard deviation from supplier B is 1.5 millimeters. And so, again, we learned what standard deviation means. So these ones would be closer to the mean. There would be a little more variability in supplier B. So it says, if the lengths of the cases are normally distributed, use the properties of a normally distributed data to explain why supplier B is not as good of a choice as supplier A. So here it's giving us kind of the beginning of our curve, but it's asking us to fill in values for the mean and standard deviation for supplier A. So as it's showed up above, the mean length of the case was 71.0 millimeters. We know that the standard deviation for supplier A was 0.33. So for our 68, 95, 99.7 rule, if we go one standard deviation above and one standard deviation below. So I take my mean and I add a standard deviation. So that's where this number comes from. 71 plus 0.33 is 71.33. 71 subtract 0.33 gets me 70.67. So within one standard deviation, so between 70.67 and 71.33, this represents 68% of our data. So now if we were to go two standard deviations above or below, so we've gone one up, if we add another 0.33, or if we take 71 and add 2 times 0.33, then we get to 71.66. If we go 71 subtract 2 standard deviations, so if I subtract 0.33 from here, that gets me 70.34. So that represents 95% of our data. Hopefully this makes sense where these numbers are coming from, because again, we're taking the mean, subtracting a standard deviation, or mean subtracting 2 times a standard deviation, or adding 1 standard deviation, or adding 2 times a standard deviation. And then finally our third, so our mean plus 3 times a standard deviation gets us 71.99. So we would go 3 times 0.33, that's how I get 71.99. And then I could go 71.0, subtract 3 times 0.33, gets me 70.01. And so that's my 99.7. So 99.7% of the data falls between 70.01 millimeters and 71.99 millimeters for supplier A. Supplier B, same idea, we're going to do the same thing. We start with the same mean. So our mean being equal to 71.0, but now our standard deviation is different. So our standard deviation is 1.5. So if I take my mean and add 1 standard deviation, so 71 plus 1.5, I get to 72.5. If I take my mean and subtract 1 standard deviation, so 71 subtract 1.5, gets me 69.5. So that's 68% of our data is between 69.5 and 72.5. So if I add another 1.5, indicating one more standard deviation higher, that gets me to 74. If I subtract another 1.5 from this, or take my mean and subtract 2 times 1.5, that gets me 68.0, I guess I can say. And so, sorry, that says 68.0. And then if I added, so took my mean and added 3 times 1.5, that gets me 75.5. If I took my mean and subtracted 3 times 1.5, I get 66.5. So 99.7% of the data is between 66.5 millimeters and 75.5 millimeters. So those are the two normal distributions for supplier A and B. I guess I didn't write this on the other one. So 99.7% of the data is between 70.01 and 71.99 millimeters. So now the question says the case should be the same length or longer than the player. If the case is too short, you can't get it on and it's not going to protect it. So we want this case to be the same length or slightly longer than the player in order to protect it. So approximately what percentage of the cases from each supplier are less than the required length of 70 millimeters? So what I'm actually going to do is just take us back to the graphs that we have, even though it is below there. So if we go to our graph for supplier A, so we see at 3 standard deviations, it was just over 70 millimeters. So we could kind of give our estimate that these cases are too short. So that's about 0.15%. Then if we look at the next one, so 70, so one standard deviation is 69.5. So it doesn't really matter, maybe somewhere right there, something like that. So all of this would be too short. That's a lot, right? We have part of 34, we have 13.5, we have 2.35, and we have 0.15. So that's a pretty significant amount. I guess they didn't include any of the 34 in their little chart here, but this is 69.5. It would actually be a little bit of this as well would be included in it. These are all too short. So that means if they sold them, people would return them because they wouldn't fit, or hopefully they would have some quality control and they would have produced all of these and then just thrown them out, which is a giant waste in terms of production. So like we said on that first one, 0.15%. Whereas with this one, if we added up all the bars to the left, this is only this part plus this part plus this part is 16%. But we know that I also said you'd actually have to add a little bit of this as well. So it's at least 16% of it are way too short, and therefore you'd have to check them out. So this is why you'd probably want to go with supplier A, because supplier B will have far more cases that are too short and therefore will be returned by customers or hopefully wouldn't have been sold at all. So that's the end of the lesson. On page 26, 27, and 28, there are a couple of questions that it's asking you about the normal distribution, and you know as well, I recommend the textbook questions as well. So that's your work for today. We'll see you guys tomorrow for the lesson on what we'll call standard normal distributions and how we can get a little bit more information out of these types of charts. All right, thanks guys. See you later.